Okay, so let's take a peek at our measures of center, or sorry, our measures of spread or dispersion. I'm going to use a smaller data set because some of the formulas we're going to look at here might be more complicated, or it will be more complicated. So let's do just, and I'm going to put these in order from smallest to largest just to make it easy on us. Let's do 11, 15, 16, 18, let's see what I have there, 25. There's my data set. My first measure of spread or dispersion is something called the range. And the range is just the largest, or what we call the maximum, minus the smallest, or what we call the minimum. So the maximum here is the largest of 25, minus the minimum of 11. Now, one of the weaknesses of the range, or to demonstrate the weakness of the range, I'm going to create a new set. What's the range of that set? Yeah, it's exactly the same. It's 15 minus 11, or 14. Would you say that this is spread out the same amount as this one? No, it looks like it's way more spread out. All the data points, if we did a number line, this one, all the data points would be out at the ends and none in the middle. This one here, they're kind of more in the middle. They're less spread out. So the range is a nice quick measurement, but it's not terribly accurate or terribly precise as far as distinguishing between data sets. So we generally use a more precise one called the standard deviation. Now, the standard deviation is a really ugly formula. We're going to assume we're talking about a sample. The standard deviation of a population is slightly different. But if we're talking about the standard deviation of a sample, and I'm going to give you the formula, and then I'm going to show you an easier way how to do it, just so you know. It's the square root of the sum of x, that's each value, minus x with the little bar over it is the symbol for the mean of a sample, squared. So you take those numbers, you subtract them, and you square them, each of them. And you divide that by n minus 1, and then square root it. Okay, that's, like I said, kind of an ugly formula. So let's do this step by step. So let's take these numbers here and take them through the steps. Step 1 is to find the mean of the numbers. So I'm going to add them up. 11 plus 15 is 26, plus 16 is 42, plus 18 is 60, plus 25 is 85 over 5. Does that turn out to be correct? So we get a mean of 17. Step 2, to subtract the mean from each number. So I have 11, 15, 16, 18, 25. And a mean is 17. I'm going to subtract 17 from each of them. So 11 minus 17 is a negative 6. 15 minus 17 is a negative 2. 16 minus 17 is a negative 1. 18 minus 17 is positive 1. And 25 minus 17 is 8. Now, if you wanted to double check yourself at this point, if you add those all up, they should add up to 0. If they don't add up to 0, then there's either your mean is wrong or you subtracted one of them wrong. Step 3. Square each of those differences. So square each difference. So -6 squared. Now remember, in a lot of your calculators, if you square a negative number, you have to put it in parentheses or it'll come out negative. Any number squared has to be positive. -6 squared is a positive 36. So make sure you put that in parentheses. -2 squared is a positive 4. -1 squared is 1. Positive 1 squared is 1. And 8 squared is 64. Step 4. Find the sum. Add those numbers up. So if I add those up, I have 106, it looks like. Step 5 is a key step. Step 5 is divide by n minus 1. Well, n equals what in this set? How many numbers were in the set? 5, right? So n equals 5. So that means that n minus 1 equals 4. 5 minus 1 is 4. So that means we're going to divide by 4. So we get 26.5. That number, by the way, would be what's called the variance. If we were asked for a variance, that's what we would give. Standard deviation requires one more step. Step 6. Square root. Now be very careful. It's not squared, it's square root. So we're going back the other direction. The square root of 26.5 is going to be 5.15, it looks like. Make sure on the test, by the way, you look when you're doing a square root, look to see what it asks you to round it to. Every semester there's a few people that lose a point for not rounding it correctly. Any questions? Now let's compare that to this other set. 11, 12, 13, 24, 25. We would expect to get a larger standard deviation, more spread out. So step 1, we're going to find the mean. 11 plus 12 is 23, plus 13 is 36, plus 24 is 60, plus 25 is 85, divided by 5. We get 17 again. Step 2, we're going to subtract the mean from each. So we subtract 11 minus 17 is still -6. 12 minus 17 is -5. 13 minus 17 is a -4. 24 minus 17 is 7. 25 minus 17 is 8. Again, if we wanted to double check, we could add those up, make sure we get 0. What is step 3? Square each of them. So, -6 squared is 36. -5 squared 25. Negative 4 squared is 16. 7 squared is 49. 8 squared is 64. What is then step 4? Find the sum. If we add those all up, we have a huge number. I'm getting 190. And then we divide by n minus 1, which is going to be 4. Which is going to be what? 47.5. And step 6, square root of 47.5 will be 6.89. So compared to 5.15, yes, it is telling us that that data set is more spread out. So what good are all these? What are they really telling us? What would we really use them for? Well, there are actually a lot of things we would use them for. But some of the simpler things that we might use them for back on the bell curve, there's something called the empirical rule. And the empirical rule, there are a couple of different versions of the empirical rule. I don't remember for sure now which one your textbook uses. I think your textbook uses a detailed empirical rule. I'm used to using an approximate empirical rule. So the numbers I use here may be just slightly different, but I'm using the simple version of it just because it's easier to remember, and in practice it's close enough. But what the empirical rule states is the center of this bell curve, if we have a good set of data, normally distributed set of data, the center of that bell curve will be either the median or the mean. They should be about the same. So we're going to use the mean is what we usually choose to use. Then we go out towards the left or towards the lower numbers on that curve in 3 steps. Each step is subtracting 1 standard deviation. So I can subtract 1 standard deviation. I can subtract a 2nd standard deviation from the mean. And I can subtract a 3rd standard deviation from the mean. And going in the other direction, we do the same thing, 3 steps, adding a standard deviation each time. So plus 1 standard deviation, plus 2 standard deviations, plus 3 standard deviations. And I'll show you what that means down there in just a minute. I'll put an example where we put real numbers in it. But the important part is what's going to go in up in the curve here. These percentages are always the same as long as the data is normally distributed. Between the mean and 1 standard deviation on either side, there's 34% of the data. Between 1 standard deviation and 2 standard deviations on either side is 13.5%. Between 2 and 3 standard deviations on either side is 2.35%. And beyond 3 standard deviations on each side is only 0.15%. I think the book uses numbers like 34.2 and 13.35 or 38 or something like that. They're just a little bit more exact than the ones I have here that are rounded off. So what does that mean? Well, let's say that on the next test, that the mean score is 88 with a standard deviation of 4. Well, that means the mean is 88. One standard deviation below, subtracting one standard deviation or subtracting 4 would be 84. That's telling me I expect 34% of the students to score between 84 and 88. Subtracting another standard deviation would be 80. I'm expecting 13.5% of the students to score between 80 and 84. Subtract the 4 again would be 76. I'm expecting only about 2.35% of students to score between 76 and 80. Does everybody see where these three numbers came from? The 84, the 80, and the 76. Any questions on that? So I just started with my mean in the middle and I subtracted the standard deviation at each step. So going the other way, I add the standard deviation at each step. What's going to go here then? 92, 88 plus 4. What's going to go here? 96, and here? 100. So, what percent of students would we expect to be greater than 92? Well, here's 92. Add up all those percents, it should add up to 16%. Now, since 80 is passing, what percent would I expect to be greater than 80? Well, here's 80 right here. If I add all of those up, oops, that's wrong. I should get 97.5%. Does that make sense? So how is this useful? Well, let's say you are looking at two different jobs. Job A and Job B. Unfortunately, they're in two completely different geographic regions. So you're going to be moving. And of course, yet when you consider pay, you can't just, or you consider a job, you can't just consider the dollar amount of the pay, you have to consider cost of living. So what we're going to do is we're going to compare other salaries in that area. So let's say in the first job A, you are being offered $38,000 a year. Job B, you are being offered $33,000 a year. But in the area of job A, the mean salary is, let's say the mean salary is, we're going to put it at 54,000 with a standard deviation of $8,000 in the field that you're working in. In area B, the mean salary is let's say $42,000 with a standard deviation of 9,000. Let's make that a little bigger. So in this curve, the percents are going to be the same, period. So 34%, 34%, 13.5%, 13.5%, 2.35%, 2.35%, and 0.15%, and 0.15%. That'll be the same over here. I'm going to leave the percents off and just do the numbers. What's going to change, of course, are the numbers down below. In this area, the mean is the 54,000. I'm just going to put in 54. And a standard deviation of 8, so I'm going to subtract 8. So this would be 46. 38 and 30. Add 8 going this way would be 62, 70, and 78. Over here, the mean is 42, so 42 is going in the middle. Standard deviation of 9, so I'm going to subtract 9. So 33, 24, and 15. Adding 9 would be 51, 60, and 69. So over here, you were offered 38,000. That would be right here. If we add these up, you are only earning more than 2.5% of the population there. So only 2.5% earn less than that offer. Or the other way of putting it is 97.5% earn more than that. Over here, your offer was 33. That's right here. If I add that up, 16% earn less than that. Or 84% earn more. So this offer over here is definitely the better offer in comparison. Now, it might be kind of depressing saying, well, 84% of the people still earn more than me, but if this is your first job or starting out, your entry level, so you have to expect to be a little bit on the lower end. It may have been better to compare to other starting salaries or whatever for instead of all salaries. Now, another example I like to use in more of an everyday life type situation. So let's say you do pick your job and you're going to make a move and you're looking at houses. Looking at 3-bedroom, 2-bath homes. And in the area you're looking, you do a little research and you find that over the last several years, the mean selling price of a 3-bedroom, 2-bath house in that area is $128,000 with a standard deviation of $16,000. You find a house that you really, really, really like that is priced at $160,000. What number is going to go in the center of this curve down here? 128, the mean. What number is going to go here? 112, right? Then here? 96, and here 80. Good. Going the other direction. What number's going to go here? $144. How about here? $160 and $176. And these percents, of course, stay the same. I want you to think for a second before I say any more. What does this tell you about that house that you found for $160,000? So $160,000 is going to be right here. If I look at these numbers, I add them up, that's 2.5%. What that's telling me is, in that area, only 2.5% of 3-bedroom, 2-bath houses cost more than $160,000. In other words, 97.5% of the houses cost less. Think there's a pretty good chance we'll find something that we like that's cheaper? Yeah. Very similar to what we've been looking at here with the empirical rule is something called a Z-score. A Z-score, I mean, you notice I had to be kind of careful here to choose numbers that fell right on one of these steps. The Z-score allows us to go in between those steps and still compare things. What the Z-score does is it's called standardizing data. It allows us to compare curves that are different from two different populations, but compare them fairly. So for example, all of you had to take some sort of admissions test or placements test to get in here. So let's say that on your math test you scored 46. And on the English or language portion of your test, you scored a 62. Your reflex might be to look at that and say, hey, we scored a lot better on the English. But what if I told you that the mean score for the math was 40 with a standard deviation of 4, and the mean score on the English was 51 with a standard deviation of 8. Now you might be looking at this and saying, well, this is only 6 points above the mean and this is 11 points above the mean, so this still looks better. But the distance might not be the same because the data for the English is more spread out. So what the Z-score does is we standardize it for each value by taking the number, we subtract the mean, and we divide by the standard deviation. So for your math test, the Z-score is 46, that's your score, minus the mean of 40 divided by a standard deviation of 4. Well, 46 minus 40 is 6, divided by 4 is 1.5. What that is saying is you are 1.5 or 1.5 standard deviations above the mean. So you think about that curve. 1.5 puts you somewhere in here. So that's the number, that the percent that would score better than you. We don't have that percent because it's not on one of our steps. But the Z-score for your English test, you scored a 62 where the mean was a 51 and the standard deviation was 8. So 62 minus 51 is 11, divided by 8 is 1.375, or 1 3/8 if you want to leave it as a fraction. That is saying you scored 1.375 standard deviations above the mean. So if you're looking on the curve up here, that'd be somewhere in here. So you actually scored slightly better on the math than you did on the English, compared to the rest of that population. Well, how can this be used? Well, a couple of ways it can be used. One example I like to use is evaluating an employee. And it's always easy to go with sales because there's easy things to measure there. So let's go with a sales job. Say a manager of a department store has to fire one of their salesmen, people. And they have it narrowed down to 2. We're going to call them Bob and Steve. And the manager decides that whoever has the worst sales week the next week is going to be the one that goes. Bob has sales of $1,400. Steve has sales of $3,200. But that doesn't necessarily mean Bob is out the door, because let's say that Bob works in toys and Steve works in electronics. Well, electronics are usually more expensive than toys, and depending on the time of year, the demand could be very different. So let's say that in toys, the mean of all salespeople in toys was $2,200 that week, with a standard deviation of 300. Let's say the mean for all people in electronics was $4,000 that week, with a standard deviation of $500. If we find the z-score here for Bob, Bob sold 1,400. We subtract the mean of 2,200, and we'll divide by the standard deviation of 300. 1,400 minus 2,200 is a negative 800. Divided by 300 is a negative 2.67. Negative 2 2/3. Bob was 2 2/3, or 2.67 standard deviations below the mean sales for toys. Steve's z-score, well, Steve sold 3,200 minus the mean of 4,000 divided by standard deviation of 500. Well, 3,200 minus 4,000 is a negative 800 again. Divided by 500 is a negative 1.6. So Steve was 1.6 standard deviations below the mean. So that's telling us that Bob is definitely the worst salesman, or had the worst results that week. You could also use this for comparing pricing. Let's say you want to compare cost of a blood test and the cost of just a standard visit, standard office call. So it's a national average, national mean for a blood test is $120. With a standard deviation of $25. The national mean for an office call is $90. With a standard deviation of $15. And let's say the place you are looking at charges $160 for blood test. $110 for an office call. Which one is more out of line? Or more expensive if you want to look at it that way? Well, for the blood test, it's 160 is the value minus the mean of 120 divided by a standard deviation of 25. So it's 40 over 25 or 1.6. So the cost of a blood test is 1.6 standard deviations above the national average. For the office call, the cost is 110 minus the average of 90 divided by 15 is our standard deviation. 110 minus 90 is 20. Divided by 15 is 1.33. Cost of an office call is 1.33 standard deviations above the national average. Any questions on that? So that Z-score allows you to compare two things that are not really in the same group, but you can compare them. Basically what you're doing is you're comparing them back to their own group. This is saying compared to the group of all blood tests, this is 1.6 standard deviations above the mean. Compared to the group of all office calls, 1.33 standard deviations above the mean. So by comparing them back to their own group, then you compare them to each other by how they compare to their own group. Last thing I want to talk about for us is percentiles. Percentiles, we used to hear them a lot. You probably still do if you have kids in school, or if you remember doing standardized testing in school. You might have been told that you placed in the 92nd percentile. Well, what does that mean? That means that you scored better than 92% of all the people who took the test. So if you have a child and they say that your child is at the 50th percentile for their height, what does that mean? They're right in the middle. The 50th percentile should be average. That means their average height for their age. So working with percentiles a little bit, we're going to need a group of numbers again. I am going to put them in order from smallest to largest. Normally, that would be the first step you would have to do, is to put the numbers in order. But since we're running a little short on time, I'm going to do that for us here. So there's my group of numbers. To find a percentile, in other words, what percentile is let's say 30. Well, 30 is not in this group. But compared to this group 30, the percentile is equal to the number that are smaller plus the number that are equal divided by 2, all divided by n. In other words, the total number. So 30 would be right here. How many are smaller? 6, it looks like, right? So there are 6 that are smaller. How many are equal? None of them, right? So 0 over 2. That's going to be divided by, well, there's 10 numbers. It's going to be divided by 10. So this is 6 plus 0 divided by 2, that's just 6. Divided by 10 is 0.6. Change to a percent, that is 60%, or the 60th percentile. What percentile is 25? Well, here's 25. How many numbers are smaller than 25? 2. How many are equal to 25? 1. So it's 1 over 2. All divided by 10. So 2 plus 1/2 is 2.5, or 2.5. Divided by 10 is 0.25. That is the 25th percentile. Find what number is a percentile. Well, let's find what number is the 60th percentile. Now up above, we just calculated that 30 would be the 60th percentile. But because this is a small set of data, what we calculate down here will probably not be the same. We're probably not going to get 30. This is going to work a lot like our median calculation. We're going to find the position. We're going to find that position by taking 60% is 0.6 as a decimal times n. In this case, n is 10. We get 6. What did we do when we got a whole number here? Remember, for the median, it was a whole number. That meant it was between that one, the 6th one, and the next one, which is the 7th one. So the 6th number is 29. The 7th number is 32. Well, 30 is between there, but it's not in the exact middle. What we're going to calculate here, we're going to do 29 plus 33 divided by 2 is 31. So the 60th percentile is 31. What is the 45th percentile? So the position is going to be found by doing what? .45 times 10, which is 4.5. When that's a decimal, what do? We round up. So it is the 5th position. The 5th position is 28. So 28 is the 45th percentile. Any questions? So next week, all that we're going to do is the test. I always get asked, can we do corrections on the last test? And yes, you can, but I realize with the time crunch, it's going to be tough. Make sure that you are doing corrections on test 4 and get them to me by the end of class next week. Test 5, I tried to write it easier so that most people don't have to do corrections. I think last semester, the average test score on test 5 was 96. So usually, like I said, I wrote it kind of short and easy so that we don't have to worry about corrections. But you certainly may, if you want to stick around and For those of you here, if you want to stick around and have me grade it right away and take it so you can correct it. Those of you at the far sites, I will try to grade it and get it back to you right away. Sometime Friday afternoon yet, if they get to me Friday afternoon early. Okay, anybody have any questions on statistics before we shut her down for the day?